All right, now that we've gone through naked statistics, let's dive into OpenIntro chapter 2.1 and 2.2, and we'll be skipping chapter 2.3. So a scatter plot shows paired numerical data where there is one point representing each individual case. These are really useful for spotting whether the relationship between two variables looks linear or nonlinear, positive or negative, or if there's no relationship whatsoever. Now, scatter plots are a common way to represent the relationship between two variables, and they're great for readers to visualize that relationship. You can see one here on the left. We have a negative relationship here between the two. This is a cool scatter plot where they changed the size of the dots to represent the size of the unit of the observation. So now dot plots are a little bit simpler. These are essentially a one variable scatter plot. So the mean here is the balancing point of the distribution. In the textbook, they show a triangle, but we have all the observations just laid out here because we're only looking at GPA. We're not comparing it with anything else. So the mean is going to be at the spot that kind of balances it. If we imagine this like it's on like a seesaw, that would be where the mean is. So the sample mean we denote with X bar, and we have the formula for it here. We have X1, X2, all the different observations, and then we divide that by the number of observations. Mu, the Greek letter mu, is the population mean. Now, in this class, we're typically going to work with X bar, with the sample mean. And we'll use that to estimate the usually unknown population mean because we don't have the data for the entire population. We'll just have a sample of the population. Now, it's common for students and even non-students, practitioners of statistics, to use these interchangeably, either because they don't know or just on accident. It kind of slips, but it's important to remember that mu is a parameter. This is fixed, but it's usually unknown. And X bar is a statistic. It's computed from a sample of the entire population, and it can vary from sample to sample. Now, something else we talk a little bit about is the weighted mean. So simple mean treats each observation equally. So right here, all of these observations are being treated equally. A weighted mean is going to account for the group size. So for example, if we're averaging per capita income across all over 3,000 counties in the United States, by simply averaging the county figures, that gives us $26,000 and some change. But if we weight each of those observations, each of the counties by their population, that gives us the true US per capita income of $30,000, like 861. So small counties being weighted the same as large counties with millions of people in that first figure, and that gives us a less accurate measure of the true average. So a histogram will bin continuous data and plots the counts or the proportions in each bin. So it trades the dot plot's exact value detail for more readability for larger data sets. Because for larger data sets, dot plots can be really, really difficult to read. In the textbook chapter, you see there's examples with smaller data sets, maybe 50 observations, and it gives you a lot of good information. But when you get a data set up to like 50,000 observations, it gets really unwieldy. It can be difficult to see a dot plot. And that's where histograms are really useful. So again, instead of plotting each individual observation, we place each observation into a bin. And then we represent the number of observations that fall within that bin as the height. So a taller bin has more observations within that range than a shorter bin. Now, there's no golden rule for the bin width. As researchers, it's really up to you to choose what you think is the best. And you're going to want to choose what's the best for the data that you have. So here we see 4 choices for histogram for the different bin widths with the same exact data. So right away, the first one should jump out to you as bad. We only have 2 bins. That's really not telling us much information. The second one looks a little bit better. It shows us the data has a sort of skew pattern to it. But when we zoom in even more for the third one down here and the fourth one, we see a lot more detail, how much detail the second one is lacking. Again, there's no hard and fast rule for you to go through, But right here, we can see after trying a couple different options, that number four is the best. It gives us some data where we see an increase early on and then a decrease over time and a couple of outliers. Now, when we look at the shape of distribution, um, one of the important things to focus on is skewness. There's a couple other things that the textbook chapter talks about. These are all important, but I want to highlight skewness because it's easy to mess this up. So the skew is named after the direction of the long tail, not where the hump is going to be. So distribution with a long tail stretching to the right. So most of the data is bunched on the left with a few large values trailing off to the right is right skewed. So right here, this is right skewed because we have the outliers sticking out here to the right. So even though the peak, so the mode, the most frequently observed value is going to be on the left side, we're carrying, when we're defining skewness, as where the outliers are located. So the interest rate histogram in reading is the textbook right skewed example. Most of the loans cluster at the low rate with a thin tail of super high rate loans. Now the mode is the most frequent observation. There are a couple different types of what we call modal. So we have unimodal, which has one prominent peak, bimodal with two prominent peaks, and multimodal if there are more than two. Prominent doesn't have a really strong, rigorous definition. Modality is about the qualitative shape of the data. So you're kind of just like describing it. So if you mix together student heights, like elementary school students and adult heights, you probably see two peaks, one for the most common height for the kids and one for the most common height for the adults. But we're not strictly counting each local bump. All three of these right here are different skewed distributions. They all have different skews, but they're all unimodal since there is a single peak. Even though this one right here has two bins right next to each other that are the same height, they're right next to each other. So there's really just one peak. Now let's think about variance and standard deviation. Um, so when we're thinking about variance and standard deviation, we're thinking about how far a specific observation is from the mean. So the variance is the average squared deviation. The standard deviation is the square root of the variance. And by using the square root, that kind of brings us back because see here in this, the variance, it's squared. We take the square root, that brings us back to the initial scale or units. We use standard deviation to explain data. We don't use the variance. I had a stats teacher in high school, and she said the reason why we place such a strong emphasis in textbooks on the variance is because when you calculated it by hand, that was a very important step. Nowadays, we just punch it into our calculators or we do it in Excel, so we really don't need the variance the same way that we used to. But it's still something that we talk about because it's important conceptually, and it makes the formulas looking at them a little bit easier, just a little bit. Now, we have n minus 1 in the divisor here instead of n. The sample variance divides by n minus 1 instead of n. The book calls this mathematical nuance, and that it makes a sample statistic more reliable and usable as an estimate of the population variance. You don't need to know the full duration of why we use the formula that way for this course, but you should know that n minus 1 is used for a sample, and it slightly inflates the variance or the standard deviation compared to dividing by n. So we're kind of correcting for the fact that the sample's own mean is closer to the data than the true population mean would be, just because there are fewer observations and stuff. Oh, and there we have figure. Sorry about that. Oh, yes, and here we just have an example showing how you would calculate the raw variance and then just take the square root of that for the standard deviation. Moving on to box plots. A box plot summarizes 5 numbers and displays them for you. So you could see the minimum value, the first quartile, the median, or the second quartile, the third quartile, and the maximum value. Plus, it flags outliers individually, so you can see if there are a lot of outliers, a few outliers, if they're really sticking out, if they're really close. So Q1, the first quartile, is 25th percentile. So 25% of the data is smaller than Q1. Q3 is the 75th percentile, so 75% of the data falls below that and is smaller than the third quartile. The interquartile range is a mouthful. It's just Q3 minus Q1. So it's the width of the box in the box plot. And it captures the middle 50% of the data, between 25% and 75%. Now, when we create the whiskers on a box plot, the whiskers extend to the most extreme data point that is still within 1.5 times the IQR of the box. Anything beyond that is plotted individually with a dot as an outlier. This is the standard, most testable definition of an outlier in this course. So if we look at the example box plot on the bottom right here, we can see the box, which has 50% of observations within this box. That's Q3 and Q1. We have the median in the middle right here. That's Q2 or the median. It's right in the middle of the box here. This just happens to be the case for this example. It's not always going to be the case. If the data is skewed, it will be either up here towards Q3 or down here towards Q1. Then we have the whiskers here extending out. We notice at the top here, it sticks farther than the bottom. The bottom because this is the lowest data or the farthest data point towards the bottom. It's not quite at 1.5 times the IQR. This line up here is at exactly 1.5 times the IQR. We know that because we have outliers that extend beyond that, and we've plotted the outliers with individual dots showing where those observations lie. So moving to robust statistics, what robust means is that it's not sensitive to extreme observations. So that means that the median and the IQR, the interquartile range, are more robust to skewness and to outliers of mean and standard deviation. This means that they're less affected by outliers. So robust means, in practice, that they barely move even if the most extreme value changes a lot. So in figure 2.12 in the text, moving the largest interest rate from 26.3 up to 35% left the median and the IQR completely unchanged. One or two very extreme observations are not really going to impact the median or the IQR. On the other hand, the mean and the standard deviation are not robust, meaning that same shift will noticeably change the mean and the standard deviation. So when an extreme value changes, that's going to impact the mean and standard deviation because every observation enters a calculation directly, unlike the median and the IQR. So why does this mean versus median and which one is robust or not robust matter practically for you and for your work? So when a distribution is strongly skewed or has really large outliers, so the example in exercise 2.17, the coffee shop income, where there are two very high incomes that push the mean from 65,000 to 73,000, while the median barely even moved. So the median and the IQR give a more representative picture of the typical case that you're dealing with in your sample, in your data, while the mean and standard deviation are more appropriate when you care about totals or you need to account for every observation. Think like total revenue or total capacity planning. And think back to the different scenarios we talked about in the naked statistics chapter, where applying the mean was more appropriate than applying the median and vice versa. For some sorts of data, for some sorts of questions, you want to use the mean, even though it's more affected by those outliers.